Okay, gentlemen, we start today the study of power system stabilizers. Last time I have introduced the function of power system stabilizer, and we have seen actually that the power system stabilizer is provided to damp the electromechanical modes of oscillations. Okay. And in order to provide the required damping to the electromechanical mode of oscillations, we provide power system stabilizer. The structure of the power system stabilizer is shown here. This power system stabilizer is given the name delta omega power system stabilizer. The reason for giving this name as delta omega power system stabilizer is that the input signal is derived from the deviation of the rotor speed, right. Now, it has primarily three blocks. The first block we denote as K stabilizer, it is the gain block. The second block is denoted as S times T W or 1 plus S times T W. This is called washout block. The third block, in this particular case we have shown two transfer functions, right. These two put together will form the phase compensator, because the power system stabilizer is to compensate for the phase lag between the exciter input to the air gap torque, okay, and to produce a torque in phase with the speed deviation, right. This power system stabilizer is to be designed so that we compensate for the phase lag of the system. That the phase lag of the system is the phase lag of the exciter and the synchronous generator. Now, I will now discuss in detail the role of different blocks of the PSS. Let us first start with the washout block. This washout block is provided to allow the high frequency signal of interest to pass and not to allow the steady state deviation to pass and change the terminal voltage, because if this block is not provided, then if there is a steady state change in the rotor speed, then this steady state change will be reflected in the terminal voltage change. Now, if you look here at the transfer function of this block, under steady state condition S is 0, under steady state condition S is 0. Therefore, when I substitute S equal to 0 in this transfer function, right, then the gain of this block becomes 0, right, and therefore, any signal which comes into the power system stabilizer, there will be no output coming from this block. However, when the frequency of oscillation of the rotor is such that if this term 1 plus S T omega, right. Now, this term will become, or you can say that it becomes for S equal to j omega, right. This transfer function of the washout block can be written as j omega T W divided by 1 plus j omega T W for any frequency of oscillation of the rotor. Now, if magnitude of this term is j omega T w is very large as compared to 1, or I can say if omega T w is very large as compared to 1, right. In that case, this transfer function has a gain equal to 1, because this 1 can be 1 is 1 plus j times omega T w can be written as j times omega T w, and therefore, this transfer function will behave as if its gain is equal to 1, right, and therefore, the speed deviation signal, right, will be allowed to pass, right, and therefore, this washout block is also known as high pass filter, okay. And generally the characteristic of this washout block will depend upon the value of time constant T w, right. In the literature, a lot of studies have been done on the choice of T w. We have also studied the effect of variation of T w, and we found actually that this T w is not very critical, and one can choose the value of T w in the range of 1 to 20, in a wide range, that is T w equal to 1 second right up to 20 seconds they have been chosen. Now, generally the time constant T w equal to 10 second is considered to be quite suitable. Further, actually sometimes what happens is that the system gets islanded, because suppose there are major faults in the system and you resort to islanding. In that case, what will happen is the frequency of this islanded system may go up or go down, and at that time this frequency is a steady state deviation, right. At that time also we do not want actually this PSS to create any problem in terms of variation of terminal voltage, right. Therefore, when you take T w equal to 10 or around that, right, then the desired characteristic of the washout block is obtained. The next transfer function block which you have to consider is the phase compensator. Now, here I have shown two stage phase compensator. There are two stages which I have shown here. It is normally called two stage phase compensator. Okay. Now, I will discuss how to design one stage phase compensator, and in case you require to provide two stages, then the second stage can also be designed accordingly. The basic function of this phase compensator is to provide phase lead, right, and therefore, we normally call this as a phase lead controller or phase lead compensator. Now, in order to provide the phase lead, this time constant T 1 should be greater than T 2. Okay. Now, I will further discuss how the phase lead controller is designed and how this can be physically realized using operational amplifiers, because when you want to realize this phase lead compensator, right, for implementation, okay, then we have to see that how this transfer function is physically realized using operational amplifiers. Although there are other ways to realize this transfer function, right, but the modern practice is to make use of operational amplifiers. Now, when we design the phase lead compensator, we have to be very careful and design in such a fashion, so that it provides the damping to the oscillations, right, which are local modes of oscillations and inter area modes of oscillations, because we have seen earlier that local modes of oscillations have a frequency range of around 0.7 to 2 hertz, okay, while inter-area modes of oscillations have a frequency of the order of 0.1 to 0.8 hertz. And therefore, if you look the total spectrum, right, the frequency range over which we want to produce damping is varying from 0.1 to 2 hertz. And the phase shift or phase lead controller is to be designed so that we get the required phase compensation, right. But as we know, as we have seen actually, that you can design this phase compensator to compensate exactly the phase lag of the system at one particular frequency. Okay. Now, further we have to understand very carefully that the phase lag of the system is not constant. It depends upon the system operating condition and system parameters. Okay. And therefore, as the system operating condition changes, the phase lag characteristic of the system also changes, and therefore, actually the design of the phase compensator so that it meets the requirement over the wide range of frequency is a real challenge. Okay. Now, this phase lead compensator, the transfer function of the phase lead compensator can be written in this form. In general, I am just putting a general, any phase lead compensator can be written as a gain K C into 1 gain K C multiplied with this transfer function, that is S plus Z 1 divided by S plus P 1. This Z 1 is the 0 of this transfer function and P 1 is the pole of this transfer function. And for this transfer function to provide the phase lead, P 1 should be greater than Z 1. Okay. Now, here to realize this phase lead controller or phase lead compensator, the simplest arrangement for its implementation using operational amplifiers is shown here. That is, in this amplifier, in this portion of the operational amplifier circuit, this is the feedback impedance portion and this is the input impedance, right. Now, in the feedback portion we have taken a circuit comprising of resistance R 2 in parallel with capacitor C 2. Similarly, in the input a circuit is comprising of a resistance R 1 in parallel with C 1. Okay. Now, we all know actually that when you use one operational amplifier, right, there is a phase inversion. Okay. Therefore, to correct for this phase inversion, we make use of one more stage of operational amplifier, so that we correct this phase inversion, because this will, in this particular case, the gain is 1 or the feedback resistance is taken same as the input resistance. So, that the gain of this operational amplifier is 1 and the phase shift is 180 degrees. Therefore, the phase shift created by this operational amplifier is corrected by second operational amplifier. The transfer function relating the output voltage E O to the input E I N can be simply obtained by writing the operational impedance of this R 2 C 2 in parallel and R 1 C 1 in parallel. Suppose you have a circuit in comprising of a resistance, a capacitance C 1 and a resistance R 1 right. I can call the operational impedance of this as Z1s. This will be equal to parallel combination of these two impedances, that is R1 in parallel with 1 upon C1s divided by R1 plus 1 upon C1, right, which can be simplified and put in the form R1 divided by 1 plus R1 C1 S. Okay. Similarly, you can write down for the feedback impedance, that is, I call this a feedback as Z2 as the operational impedance of the feedback impedance, that can be written as R2 divided by 1 plus R2 C2 S, and therefore, we can write down the transfer function EO divided by EIN, EOS divided by EINS as it is ZF divided by Z1. ZF is here, this quantity, and Z1 we have already. Therefore, when you divide, it will come out to be 1 plus R1 C1 S 1 plus R2 C2 S, this multiplied by R2 by R1. Okay. Therefore, you can see here actually the transfer function is similar to what we are looking for, because we are interested in having a transfer function of the form 1 plus T1 S divided by 1 plus T2 S. Therefore, this simple operational amplifier with the feedback comprising of a resistance in parallel with capacitance. Similarly, input also a resistance in parallel with capacitance. We can get a simple transfer function, which, and by choosing the value of this R1 C1 R2 C2, right, we will in a position to obtain the required phase characteristic of the transfer function. Okay. Now, here I have written this expression which just now we derived. We call this as a GCS, that is the transfer function of the compensator. GC, C stands for compensator, as EOS by EINS. Now, this can be put in the form, the one which we have just now derived, right. It can be now put in a different form, right. That is, you can put this in the form C1 by C2 S plus 1 by R1 C1 S plus 1 by R2 C2, and therefore, we can say that this transfer function is of the form gain Kc S plus Z1 S plus P1, where you can identify the Z1 as 1 by R1 C1 and P1 as 1 by R2 C2. Okay. Now, in order to reduce the number of independent parameters of the circuit, we can choose C1 equal to C2 equal to C. That is, these two capacitors can be chosen to be equal. Once you choose this C1 equal to C2 equal to C, this transfer function can be written here in this form. It is put C1 equal to C, C2 also equal to C, and you divide this whole expression by R1 and denominator by R2. Okay. Then finally, it is written in this form at R 2 by R 1, 1 plus R 1 C s, 1 plus R 2 C s, which can be R 2 by R 1 can be written as 1 by A, where A is equal to R 1 by R 2, and T can be written as R 2 into C. Okay. Therefore, now I get the transfer function of the compensator in the form 1 by A multiplied by 1 plus A times T s, 1 plus T s, right. Therefore, what we have done is that we have now two parameters to be computed. One is the A, another is the time constant T. And as I have told you actually that T 1 is greater than T 2, and therefore, A is greater than 1. A is always greater than 1 to realize a phase lead controller. Right. Now, the problem arises is that how to choose the values of these two parameters A and T. Now, this quantity 1 upon A will be considered as part of the stabilizer gain, because this is a multiplying factor, a constant. Therefore, this can be clubbed with the stabilizer gain. Okay. Now, we will now study how to design this phase lead compensator to achieve the required phase compensation. Now, if you look here in this transfer function, yes,
A has to be less than 1, because T 1 is greater than T 2, that means R 1 is less than R 2.
no, here this, if you look at this transfer function, this portion of the transfer function, right, that this represents T 1, this represents T 2, and we want phase lead compensator, and for this phase lead compensator, this A into T should be greater than T. Therefore, A has to be greater than 1. That is, if you want to get the phase lag, then A will be less than 1, because sometimes we do require phase lag compensators in the design of controllers, right. At that time A will be less than 1, and this A equal to R 1 by R 2, the values of R 1 and R 2 can be so chosen, so that we get the required ratio. Now, the simplest approach to design this compensator is that we identified two corner frequencies of this transfer function. This transfer function has two corner frequencies. One is omega equal to 1 upon A t, call it omega 1. Another corner frequency we can call it omega 2 equal to 1 upon t. And this particular transfer function will provide you the maximum phase lead at a frequency which will be the geometric mean of these two corner frequencies, right. Therefore, here we consider this omega m as a geometric mean of the two corner frequencies, which is obtained as square root of 1 upon A t into 1 upon t. That is, these two corner frequencies we identify, we find out the geometric mean, okay, and the geometric mean of these two corner frequencies is equal to 1 divided by square root of A into t. The idea here is that when you plot for this transfer function, right, the phase angle versus frequency, right, then the maximum phase angle of this transfer function will occur at a frequency equal to omega m, and this frequency is the geometric mean of these two corner frequencies. Okay. for this transfer function, GCS for s equal to j omega, let us write down what is the phase angle of this transfer function, right. To obtain the phase angle of this transfer function, what we do is that we write down g c j omega equal to 1 upon a remains 1 plus j times a omega t, that is for s equal to j omega, 1 plus j omega t. Okay. What is the phase angle of this transfer function? Obviously, the phase angle is that phase angle of the numerator minus the phase angle of the denominator, and the phase angle of the numerator is tan inverse a omega t, and of the denominator is tan inverse omega t, and this is actually the phase angle of G C j omega. That is, for this function, for this transfer function, the phase angle is given by this expression. A very simple formula to compute the . Now, my interest is to express this phase difference, right, phase difference in a simple form, that is in terms of A and T. Okay. Now, what we do here is that we make use of this identity, that is phase angle of this function is, let us say, phi, then tan phi is equal to omega a t minus omega t divided by 1 plus omega a t into omega t. That is, we know that if suppose you have this function tangent theta 1 minus theta 2, right, this is equal to tan theta 1 minus tan theta 2 divided by 1 plus tan theta 1 tan theta 2. Okay. Now, here tan theta 1 is equal to omega a t, tan theta 2 is equal to omega t, not a, and the phase angle of this transfer function is theta 1 minus theta 2. We will call this quantity as phi. So, that now I can write down tan phi equal to omega a t minus omega t divided by 1 plus omega a t into omega t. Okay. A very simple expression of the phase angle of this transfer function. Now, we know that for omega equal to omega m equal to 1 upon square root of a t, the phase shift is maximum. Okay. And therefore, what we do here is that we write down the expression for tan phi m in this form, that is, you substitute in this expression omega equal to omega m. Okay. And when you substitute omega equal to omega m in this expression and simplify, you will find that we get an expression for tan phi m equal to a minus 1 divided by 2 times square root of a. This step you can just substitute and verify. Okay. Now, this expression is further written in the form sin phi m equal to a minus 1 or a plus 1, or a can be expressed as 1 plus sin phi m divided by 1 minus sin phi m. There we have obtained very simple expression for a in terms of the required phase angle of the transfer function or the phase compensator. That is, if I want actually that this phase compensator should provide a phase shift equal to phi m, right, then what should be the value of A? Right. The value of A is obtained by the simple formula A equal to 1 plus sin phi m divided by 1 minus sin phi. These intermediate steps can be easily verified. Right. Then we have also now an expression omega m equal to 1 divided by square root of A t. That is, if I know that this is the frequency at which I want to get the required phase shift, then omega m is known to me. I start with this omega m, the frequency at which I want to compensate for the phase lag of the system. Okay. Therefore, omega m is known to me. So, that using this expression and using this equation, because I know both the things, I know what is the phase shift to be achieved, that is how much should be the phase shift or phase lead this phase compensator is to provide. I also know at what frequency it is to provide. Okay. Therefore, knowing these two information, I have a very simple formula where first I compute the expression for A, because phi m is known to me, and then use this expression, use the value of A to obtain the expression or the value of t, right. So, that I can now, I have now both the parameters A and t both. Now, the question arises that what is the frequency at which I should design my power system stabilizer. This frequency is the rotor frequency, rotor oscillation frequency. However, this rotor oscillation frequency we have seen varies over a wide range, right. And therefore, this power system stabilizer should be designed in such a fashion, so that you design for one frequency, but when the frequency varies from that value on or increases or decreases, still it should be in a position to give you reasonable phase compensation. But I just now mentioned, I told you very clearly that we would like to design power system stabilizer in such a fashion, so that it may have some undercompensation, but it should not have overcompensation. The moment you have some degree of undercompensation, we get an advantage of additional synchronizing torque coefficient, positive synchronizing torque coefficient, and is helpful, right. But we should not target to overcompensate, because the moment you try to overcompensate, it will produce a negative synchronizing torque coefficient. Okay. Now, many times the required phase shift cannot be obtained using one stage of the phase lead compensator, and in that case we go for two stages, that is called two stage phase lead compensator. Many times one can have two identical blocks, that is, here I have shown this phase compensator, right. I have discussed how to design one stage phase lead compensator, and we can have two stages identical. In that case, suppose I want to compensate for say 85 degrees, let us say, right. Therefore, instead of designing one phase compensator to compensate for this total 85 degrees, I can design so that one is for 85 by 2, another is for 85 by 2. Generally, the thumb rule is that one phase lead compensator block should be designed to compensate around 50 degrees. To understand the basic concepts of designing the phase lead compensator or for that purpose any linear compensator. I will advise you to read this chapter 10, which is design of control systems. That is, the title of the book is Design of Control Systems, written by B.C. Koo. I am just let me correct it. Title of this chapter 10 is Design of Control Systems. The title of the book is Automatic Control Systems. The 7th edition by B.C. Koo. B.C. Koo is a very standard textbook on automatic control systems, and I am sure that you will be in a position to very clearly understand how this to be designed. Now, I will just quickly tell you how to obtain the state space model of the complete system. That is, when you have incorporated a power system stabilizer, right, automatic voltage regulator in the system, therefore, we can develop a complete state space model of the single machine infinite bus system, including AVR and PSS. We had developed earlier the state space model considering the input signal from the exciter as delta EFD. That is, this transfer function model, actually if you just look here, this transfer function model, I am sorry, from this transfer function model, that if you see this portion, actually, that is, we are not considering PSS, we are not considering the excitation system and AVR. Therefore, the state variables which are required to model the system in the state space form are delta omega r, delta delta and delta psi FD. With these 3 state variables, right, one can write down the state space model of the system, and input to this model or input to this state space model will be delta Tm and delta EFD, right. The model is written in the form delta omega r dot delta dot delta psi FD dot, and this is my x dot, and this is the A matrix A, this is the state vector, this becomes the input matrix B, and this is your input vector U, right. Therefore, in this case the input is comprising of delta Tm and delta EFD. Now, you can obtain more detailed model including the AVR and PSS. Now, to develop this model, I will just tell you few salient steps. The additional portion of the transfer function to be incorporated in the model is shown here. This is the additional portion, because we already developed actually the transfer function model of the third order system. Now, the exciter is represented by a gain Ka only. You can represent the exciter depending upon the what type of exciter you are using. Okay. We know the detailed models of the different type of excitation system. Therefore, here for the purpose of simplicity, we are representing this by a constant Ka only, and this represents the static excitation system, the IEEE ST1A model. Okay. This is the change in the terminal voltage delta Et. This is the transfer function of voltage transducer, terminal voltage transducer, that is we get a quantity called delta V1. This is the transfer function model of the PSS. This portion you can just see it. Yes, I have shown in this model a single stage phase lead compensator, right. If necessary, one can put one more stage, 2-stage phase lead compensator, right, and accordingly you can modify your state space model. Now, the question is that how do we develop the differential equations, linear differential equations for this system, so that they can be augmented with the existing, or the existing system model is augmented by adding these equations, additional equations. Now, the state variables which we will have to define, new state variables, one is, because earlier this was the only input signal here, right. New state variables which you have defined will be delta V1, which is the output of this transfer function block, Vs, output of power system stabilizer. Then here we call this another state variable, we call this as a delta V2, okay. And here there is no state variable required, because this is only a gain. Therefore, at this point it is, the signal is k step into delta omega, okay. Therefore, so far this block is concerned, in this block the input is this quantity, output is delta V2. So far this second block or phase compensator is concerned, input is delta V2, output is Vs. This block 1 is concerned, input is delta Et, output is delta V1. Therefore, these 3 state variables are required to develop the complete model of the machine infinite bus system, including PSS and AVR, right. Now, the equations can be written very easily. Let us just write the equation for first block, that is, here transfer function is 1 over 1 plus s times Tr, output of this is delta V1, input of this is delta Et, okay. Now, this model which we are talking about is a small perturbation model, and in small perturbation model all the state variables initially are 0. That is, the perturbed values like say delta V1, delta Et, right, at time t equal to 0 are 0, and therefore, we can replace S by P, okay, and you can write down the equation in this form, delta V1 equal to 1 plus S times Tr into delta Et, or you can write down here now 1 plus S times Tr into delta V1 equal to delta Et. Very simple, right. Now, here if I replace S by d by dt, S is replaced by d by dt, then you will and divide by Tr all through. You can write the equation in the form that delta V1 dot will be equal to 1 upon Tr delta Et minus 1 upon Tr delta V1. Okay. Now, to make this equation complete equation, because delta Et is not a state variable, delta Et is not a state variable, but delta Et can be expressed in terms of the state variables. Therefore, delta V1 dot is written as 1 upon Tr, delta Et is equal to K5 delta plus K6 delta psi f d, okay, minus 1 upon Tr delta V1. Okay. Therefore, now I have written one additional equation, this is a differential equation. It is expressed in terms of these three state variables, delta delta, delta psi f d and delta V 1. Okay. Similar approach is to be used for deriving additional state variable equations, right. I will just illustrate for delta V 2 also. Now, to understand how to develop the equation corresponding to this washout block, we can write down delta V 2 equal to S T W or 1 plus S times T W. Input is k step into delta omega r. Delta omega r is a state variable. Now, you perform the similar operation, you will find that S times delta V 2 equal to k step S delta omega r minus 1 upon T W delta omega delta V 2. Okay. That is, you cross multiply and then collect the terms, so that you put S delta V 2 on left hand side and all other terms on right hand side. Now, in this equation you find here S delta omega r, S is d by dt. So, that this is basically your delta omega r dot term, delta omega r dot term, because whenever you write a differential equation, on right hand side we will have only the expression which is a linear function of state variables, right. Therefore, what we do is that this delta omega r dot is replaced by this equation. We have the equation here, delta omega r dot is equal to a 1 1 delta omega r plus a 1 2 delta delta plus a 1 3 delta psi f d plus b 1 1 delta T m. We have it, right. So, that when you now substitute the expression for d by dt of delta omega r in this expression, you will get a equation for delta V 2 dot, and this delta V 2 dot is now written in terms of all the state variables like delta omega r, delta delta, delta psi f d, delta V 2 and delta T m. Because when you write this, right, this differential equation, it will be function of state variables plus input variables. Now, here input is delta T m, right. You follow the similar approach for writing the transfer function of phase lead compensator. That is, in the phase lead compensator, the input is delta V 2, output is V s. The transfer function is 1 plus S times T 1, 1 plus S times T 2, right. Now, V s is one of the state variables. So, that we can write down the equation in this form. We have to simplify the expressions following the same approach. Ultimately, our requirement is that the right hand side of the expression should be function of all state variables and input variables. The last equation is for this block, a summation block here. Now, what we do is that delta E f d is written in terms of K, that is delta E f d is equal to K into delta V reference plus V s minus delta V 1. Okay. Now, this delta E f d appeared in our earlier equation for delta psi f d. That is, if you see this equation for delta psi f d, this delta psi f d is a substitute actually the expression for delta E f d, because when delta psi f d was written, delta psi f d dot equal to, right, function of delta 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 omega r delta psi f d plus function of delta EFD. Therefore, this delta EFD is now not a state variable, is to be eliminated. Okay. When all these things are done, that is, you can eliminate this delta EFD and you will get an expression in the form delta psi FD dot equal to A32 delta delta, A33 delta psi FD, A34 delta V1, A36 Vs, AB32 Ka delta V reference. That is, what we have done here is that we have written 3 additional equations, okay, and modified the third equation that was corresponding to delta psi FD dot. Okay. And the total model of the system can be written in this form. It comes out to be a 6th order model. There are 6 different state variables, delta omega r, delta delta, delta psi FD, delta V1, delta V2, Vs. Okay. And we can write down this model in the form again x dot equal to A x plus B u. Now, this u is delta T m and delta V reference. There is input is now the mechanical torque, that is the incremental change in mechanical torque delta T m, and the change in reference voltage delta V reference, and delta EFD has now been eliminated from the model. Now, in this model, once the model is developed, we know actually that all these parameters, that is coefficient, the elements of this A matrix, they are all function of loading condition and system parameters, right. One can find out the eigenvalue of this A matrix to understand the stability of the system. Okay. Now, I will just quickly tell you 1 or 2 more points before I close the discussion. The basic limitations of delta omega PSS. Basic limitations, the limitations are, one is that this delta omega PSS can excite the torsional modes, has the potential of exciting the torsional modes. In case you have large gain of the PSS, if the PSS gain is kept large, then it can excite the torsional modes. Many times, to overcome the problem of excitation of torsional modes, we provide filter in the PSS path. The moment you provide filter, right, then this again restricts the PSS gain. That is, we cannot have the gain as much as we want, because if you want to, can say, have the desired damping, right, then the gain setting of the PSS will give you the required damping ratio, right. But if you try to design the PSS so that you achieve the required damping for electromechanical mode, right, then there are other problems. The other problems are the possibility of excitation of torsional modes and the limitation on the PSS gain. Okay. Let me sum up here that we have discussed today the details of the power system stabilizer to be applied. We have analyzed the system with PSS, okay, and we have also seen how this PSS can be realized using operational amplifiers, and at the end we have derived the complete state space model of the machine infinite bus system, including AVR and PSS. I will suggest that all of you should derive this model yourself, right, and so that you can study the behavior of the system with PSS. we can make use of the MATLAB software package to find out the eigenvalue of the system matrix and to simulate the dynamic performance of the system by giving some perturbations, maybe perturbation may be in terms of perturbation in mechanical torque. You can just make delta T m equal to some 0.01 or change in the reference voltage and see the behavior of the system. Thank you.